Hi, my name is Sukhmani Sethi, and this is my lab report for Physics Lab 3. The purpose of this lab is to apply formulas using a computational model to derive an unknown mass and an unknown initial velocity required to escape a system, and visualize the forces present in an orbital, such as the properties of gravitation. Key concepts in this lab include Newton's second law, which states that the net force of an object is defined by the change in momentum over the change in time. This is also rewritten to derive both the velocity and position update formulas. The components of net force include the parallel and perpendicular components. The parallel component, or p hat, is parallel to the direction of motion and relates to the change in speed of the object, whereas the perpendicular component, or n hat, points to the center of the orbit or the circle and is perpendicular to the parallel component, and it relates to the change in the direction of the object. The gravitational force formula, often referred to Newton's law of universal gravitation, is the equation that describes the force of attraction between any two masses or the gravitational force on an object due to another object, where the masses exert a equal force and in opposite direction on each other due to Newton's third law. The main results of the lab were that the mass of the black hole was found to be 1.44 e to the 44th, and the initial velocity was 4.1 e to the 6th in the y direction. In part 1, to find the mass of the black hole, the calculation section was edited to incorporate formulas inside the code. For example, P equals mv, so the variables for momentum were assigned to the star's mass multiplied by its velocity. After everything was filled out, the mass of the black hole was set equal to the magnitude of Fnet times r squared divided by g times the star's mass, which came from the gravitational force formula. Then the arrows were created for visual representation of the forces using the values found from coding in the calculation section. After the simulation ran, the mass of the black hole was found to be 1.44 e to the 44th as an average of the results of each iteration. The net force on a celestial object, such as the spaceship near a black hole, is the total force acting on it, determining how the spaceship accelerates. This net force is broken down into parallel and perpendicular components relative to the spaceship's motion, and the parallel component affects the spaceship's speed, whereas the perpendicular component dictates its directional change. Meanwhile, the rate of change of momentum, which is the change in the spaceship's momentum over time due to these forces, reflects how the spaceship's velocity adjusts. Essentially, while the net force shows the immediate effect of gravity on the spaceship's acceleration, the rate of change of momentum provides insight into how these forces alter the spaceship's path and speed over time. Calculate the net gravitational forces acting on both a planet and a spaceship near a black hole, and ensure that the spaceship could safely approach and then move away from the black hole without crashing. Newton's law of gravitation was used. The mass of a black hole was set to 1.44 e to the 44th as found in part 1. The forces due to the black hole and the planet were calculated and applied to update the velocities and positions of the planet and the spaceship over time using Newton's second law. The initial velocity was adjusted after running the simulation each time to find a velocity that allowed the spaceship to not crash, and it was found to be 4.1 e to the 6th meters per second. This allowed for the spaceship to avoid crashing into both the planet and the black hole despite their gravitational forces. To enter into a stable orbit around a black hole without crashing into it or a nearby planet, the spaceship would need to achieve an orbital velocity that balances the gravitational pull of the black hole. This velocity can be calculated using the formula v equals square root of gm over r. The velocity should be tangential, meaning directed along a path perpendicular to the radius connecting the black hole and the spaceship, ensuring that the motion is circular and the spaceship neither falls into the black hole nor escapes its gravity. This lab successfully applied computational models to calculate the mass of a black hole and determine a safe initial velocity for a spaceship navigating near it, using Newton's law of motion and gravitation. The experiments provided a clear visualization of gravitational forces and their effects on celestial bodies. Further simulations with more variables could offer an even greater accuracy and visualizations of orbital dynamics. For part 1, errors include that running the simulation for longer would have allowed for a more accurate average mass of the black hole, so the mass found may have been slightly inaccurate. For part 2, the initial velocity was found through trial and error, and using a formula instead would allow for the spaceship to be even closer proximity to the black hole, but still not crash into anything. And then both simulations assume that there are no other forces present in the system, but in reality there would be other forces that affect net force and the system dynamics.